Okay, this video is about inverses. So we're going to talk about relations and inverses of relations and functions and the inverse of functions. So I'm going to start off with this relation. We have x values and y values. So this is just the domain is each of these x values, and the range is each of these y values. And I'm going to go ahead and plot those. So the first one is a point 1, -1. Second one is a point 2, 0. Third one is a point 3,1, and the fourth one is a point 4,1. So this is this relation. I'm going to call this relation R for, well, R is already being used for range, so I'll call it S for some relation. Okay? So now what we're going to do is we're going to find the inverse of this relation. Well, what an inverse means is you have this line at y equals x that's kind of this imaginary line that you don't see. And what you're going to do is you're going to go exactly across that line and you're going to plot the inverse relation. So if this point's exactly across the line would be right here. This point exactly across the line would be right here. This point exactly across the line would be right here, and this point goes 1.5 squares, so let's go 1.5 squares. So here we go. In blue, I have the inverse relation of this function, and let's look and see what the values of each of these points are. So I'm going to create an xy table for my blue values. Okay, so this one is going to be -1, 1. This next one is going to be 0, 2, then I have 1, 3, and then I have 1, 4. So if you notice, these two things are the exact same. I've just changed my x and my y values. If I change y and x here, I have the exact same things, and that's what a relation does. It switches the x and y value. I mean, that's what the inverse does. It switches the x and y value for every single point of a relation. All right, let's take that and let's do something more interesting. Oh, actually, let's talk about. So if I wrote the relation and I've switched the x and the y, that also means I've switched the domain and the range, and that's going to be important in a few minutes. So let's find the inverse of this relation right here: y equals x squared plus 3. So the way you find the inverse is you switch the x and the y values. So let's do that. Let's switch the x and the y variables, and then let's solve for y again. So the inverse of this function here, let's subtract 3 from both sides. Now we have x minus 3 equals y squared. And then let's take the square root of both sides. You got plus or minus square root of x minus 3 equals y. Here is the inverse relation of this relation. Now it's important to note that this is not a function. This is a function here, but this is not a function. That's why I'm using the term relation. These are inverse relations. We're going to graph these now, and then you'll see why one of them is not a function. So I'm going to graph this one in blue, and I'm going to graph this one in red. So let's go back to the first one, and let's graph this parabola. This parabola is shifted 3 up, and then other than that, it goes through 1, 1, and it goes through 2. You go up 2, over 2, up 4. Wait, over 1, 2, up 1, 2, 3. Just kidding. These are the points. So here's the graph of the blue one, and then I'm going to graph the red one. Let's plug in a few points. Let's plug in, if x was 3, then y would be 0, so 1, 2, 3, 0. Okay, well, if x was 4, then y would be 1. If x was 5, then y would be, let's make this 4. So what do we need to plug in here to make that 4? We need to plug in 7. So 7 minus 3 would be the square root of 4, which would be equal to 2. So 1, 2, 3, 4, 5, 6, 7, 2. There's a point. Okay, so this is what it looks like, and actually I know that these are also going to be points here. So this is the parabola turned on its side, except that I can't draw very well. So this is the inverse relation. And if you looked at the line y equals x, so I'm going to go ahead and put that line on here. This is the line y equals x. these points, every single point is translated across that line. If that line was a mirror, then this is what it would look like. And that's what the inverse really does, is it reflects the original relation across the line. Now I talked about this not being a function. This one's a function right here. This is a function, check. This one fails the vertical line test at every point except for at the vertex. So this one is definitely not a function. So when you're thinking about functions and their inverses, if it fails the horizontal line test, its inverse is not going to be a function, because when you flip it, the vertical line is going to go through multiple points. So these are the graphs of the function and its inverse. I'm sorry, the function and its inverse relation. All right, so let's find the inverse of this function. So again, we're going to switch the x and the y values. I'll do it in blue. So I'm going to say x is equal to the square root of y minus 1. Now I'm going to square both sides, and I'll get x squared is equal to y minus 1. And I'm going to add 1 to both sides, and I get x squared plus 1 is equal to y. This is the inverse of this function. But if we think about the graphs, y equals x minus 1 is going to look something like this. So the inverse, when you rotate it across, isn't going to look like a parabola. It's going to be half of a parabola. And that's because the domain and the range are really important values. I mean, really important things that we haven't talked about much yet. So let's talk about that now. All right, what is the domain of this function up here? Y equals the square root of x minus 1. Well, the square root of anything has to be positive, so it has to be greater than or equal to 0. So that means x minus 1 has to be greater than or equal to 0, which is the same thing as saying x has to be greater than or equal to 1. This is a domain restriction. Well, if x is greater than or equal to 1, then the smallest thing that y can be is 0. Y has to be greater than or equal to 0. So the domain of this function is x is greater than or equal to 1, and the range is y is greater than or equal to 0. So here's the domain, and here's the range for this function. Our inverse function, I'll write that here, y is equal to x squared plus 1. The domain is going to be x has to be greater than or equal to 0, and the range is going to be y has to be greater than or equal to 1. I've flipped these two things. They're opposites of each other. So now, if I'm graphing this, y equals x squared plus 1, it's going to be a parabola that looks like this, but my domain is restricted that x has to be greater than or equal to 0, so I can't graph this side of it. And my range is going to be that y is greater than or equal to 1, and we see that here. So now when I graph the original function, y equals x minus 1, and I'll go ahead and graph it in black to make it easier, it would look like this. These are reflections of each other. So the inverse of the above function is right here, but you need the domain and the range restrictions. Okay, now we're going to talk about the composition of inverses. So we talked about the composition of functions on the last lesson, but here's a statement that in general is true. The inverse of a function, the composition with the original function, gives you whatever you put back, what you put in it is what you get out. So f of f inverse of x is going to give you x. And we'll test that, and we'll see that that's true here. So if f of x is equal to x minus 7 over 6, then f inverse of x, we want to figure out what that is. Well, f inverse of x is if you just switch these two variables. So we're going to say x is equal to f inverse of x minus 7 over 6. So we're treating f inverse of x just like we did y. So if I'd said y equals this, then I would say x equals with a y here where I have f inverse, but now that we're using function notation, you write it like this. And we're going to solve for f inverse of x. So multiply both sides by 6, and you get 6x equals f inverse of x minus 7. And now add 7 to both sides, and you get f inverse of x is equal to 6x plus 7. So this is our inverse function. So now that we have our original function and our inverse function, this should say f to the negative 1. Negative 1, that's the notation for inverse function. we can find our composition of functions. So let's find f of f inverse of 374. That's f of f inverse of 374. So that means I take 374 and I plug it into f inverse. And that gives me 6 times 374 plus 7. I'm going to use a calculator for that. 6 times 374 plus 7 is equal to 2,251. 2,251. Now I'm going to take that and I'm going to use it as the input. So this is 2,251 for f. So now I'm going to take 2,251 and I'm going to plug it in here. So that means I subtract 7 and divide by 6. Well, that's the opposite of what we just did a second ago. 2,251 minus 7 divided by 6 is equal to 374. It's the same thing that we plugged in originally. And that's because that's exactly how a function's inverse operates. It does the exact opposite of the things that the function did originally so that it gives you back the original value. It's basically undoing the original function. So when you see a problem like this, f inverse of f of negative 99 pi, the answer is going to be negative 99 pi. I don't need to plug it in to f of x in the inverse of f of x to figure out that that's true. You can check and see if it's true if you want, but it is. And also you notice that it doesn't matter if you do f inverse of f of something or you do it the other way around, you end up getting the same thing. So that's a pretty cool thing that inverses do together. The composition of inverses creates the original input. And that's it for this lesson.